Hello, everyone. My name is Eric Lentz. I'm an SDK engineer with Embrace. I've been doing software engineering for about 15 years and iOS specifically for about 10. I've worked in a ton of different industries from gaming to finance and healthcare. I was a member of the WatchKit team at Apple for 3 years. And a fun fact about me is I actually have a liberal arts degree with a minor in art history. So I might be able to explain Gothic architecture to you as well as application architecture. Maybe we'll try that next time. For today, though, we're talking about crashes. And to get started, I want to answer the question of why did we build a computer that crashes? Because if you think about it, that's kind of a weird thing for us to have built. Wouldn't it be better if they never crashed? Like, couldn't we build a computer that can never crash? So let's think about that question and answer that question. Next, I'm going to explain how programs load. Because in order to understand how a program crashes, you need to know how it got into memory in the first place and what it's doing while it's running. Then we'll explain how the program crashes. And finally, we'll tie everything together by looking at a real crash report I pulled off of my device, and we'll explain what all the fields mean and tie that back to what we've learned earlier in the talk. So first, why did we build a computer that crashes? Well, this is the analytical engine. This is an old mechanical computer designed by Charles Babbage back in 1837. It was never actually built. This is a model in the British Museum. But if you look at it, this computer is built out of mechanical parts, gears and pipes and metal, all these kinds of real world items. So if you look at that, what would you can't store more in there than you have gears already, right? There's limitations on the physical materials that this device is built out of. Those gears are only going to spin so fast. Those belts can only move so fast before they just start on fire and burn up. It's the same in the digital computers that we build. We only have so much money and electricity only moves so fast. So every computer that we build has limitations. And general purpose computing is all about dealing with those limitations. Let's look at a real example. So this is a picture of a car's odometer. It has a bunch of dials. This one has 6. So it can store a value of up to 999,999. But what happens when you go to 1,000,000 miles? Well, it doesn't have a 7th dial, so it can't show 1,000,000. And all the other dials roll over to 0, and it looks like it just came off the lot, a brand new car. The same problem exists in digital computers because we use bytes to store our data. And a byte is a collection of 8 bits. 8 bits can store a max of 255 possible values. If you need to store a 256th value, you need a 9th bit. And if you don't have it, those bits are all just going to show 0. We call this integer overflow, and it's an example of a real world limitation that still exists in the digital computers we build today. So how do we deal with these limitations? Well, we can work around them. Some operating systems will show an error message. We could show an error message on the dashboard of our car when the odometer moves to 1,000,000 miles and tell the user to take it in. We can virtualize the computer onto other hardware. Now, us iOS developers are familiar with working with the iOS simulator on our Mac. But your Mac has 32 gigs of RAM or more, while the iPhone only has 3 or 4. That means you can write a much more powerful program and it'll work great in the iOS simulator on your Mac, but crash immediately when you run it on your phone. So that's an example of working around the limitations of the hardware by virtualizing onto a larger machine. We can also handle these problems using code patterns. So you might be familiar with exception handling via try, catch, finally. So that's an example of catching an exception in your program, figuring out what you want to do, and then continuing to execute instead of crashing. But at the end of the day, the operating system has to protect itself. Just like the gears in that mechanical computer, the CPU in our iPhone can only get so hot before it physically damages itself. The operating system needs to protect that real world limitation or the user's iPhone will stop working. So at the end of the day, if you hit a limitation and you don't handle it, the operating system is going to crash your program in order to protect itself. So let's switch gears a little and talk about how programs load. So the code that you write, the code you actually type into Xcode, compiles into a binary that we call your application binary. That's a module of your application. We refer to it as a module because it's not the only one. So maybe you're using Google Analytics with your program. If so, you're linking a binary framework that Google built and distributes. That's another module of your application. If that framework is not in memory, you can't call functions in it and use its functionality. The same if you use the Facebook SDK. Most programs use a number of third-party frameworks, which we all call binary modules of their program. Additionally, an iOS program is going to require at a minimum one of the operating system frameworks like UIKit or the Swift runtime. Without that, your program can't run. That's another module of your program. But programs are really a graph, a dependency graph. Your application binary depends on the Facebook SDK to run. But the Facebook SDK actually also depends on Google Analytics to track its own data, and it depends on the Swift runtime to show alerts and UI. So the graph of your program is a dependency graph, and we can solve that graph to figure out the load order. This is the order that we need to bring the modules into memory in order for your program to run. So if you think about it, how would you call a function in the Facebook SDK if you don't know where it is in memory? So it has to be in memory first. So in this example program, the load order would be the Swift runtime, then Google Analytics, then Facebook SDK, and finally your application binary. The reason we need to solve a load order is because memory is linear. The addresses in memory are an increasing address, and this memory is just a linear array of bits that we can store data in, but each bit can only store a 0 or a 1. So we have to make sure that when we put things into memory, we leave enough space for the entire item and then put the next item in. So let's look at an example of that with this program. So the first thing we need to load into memory before a program can run is the Swift runtime. Now, modern operating systems tend to load their own frameworks like Swift and UIKit into the upper ranges of memory because those frameworks are always needed by everything in the operating system. So it makes sense to leave them in a reserved area of memory and just never let them leave memory. But the modules you linked can go into the lower orders of memory. So in this example, let's pretend that Google Analytics, which is the second module we need to load, loads at address 0. That'll make our examples a little bit easier, but the Google Analytics is not size 0, it has a size. So when we load a Facebook, we need to load it at a place after the Google Analytics framework. We need to give enough room for Google Analytics. So let's put the Facebook SDK at address F000. Now that we have the dependent modules in memory, we can put your application binary into memory. But again, we need to leave enough room for the other modules. So let's put your application binary at address F and 5 zeros. So now we have your program into memory. Let's look at how it might run. But first, let's talk about what we call those addresses, because the addresses that we choose to load those modules are very important, and you've probably seen them in crash reports before. We call that address the base address. And that's because that's the point where that module is loaded in memory. But what about functions? We want to be able to call functions in these SDKs to do our work. How do those work? Well, it's not that complicated. So here we're looking again at the base addresses of our modules and our module names, and then these are functions implemented in those modules. So for example, the Facebook SDK implements a function called entry point. That entry point is located 64 bits past the beginning of the Facebook SDK. But if you remember, we loaded the Facebook SDK at address F and 3 zeros. That means the real absolute address of Facebook's entry point is F064. Now, Google Analytics also implements an entry point. Their entry point is also 64 bits past the beginning of their framework. But because the base address of Google Analytics is 0, the absolute address of Google's entry point is just 64. So you can see how the absolute addresses are needed in order to jump around in memory. Let's take a quick look at what a DSym is. I'm sure you've experienced DSyms. They've probably caused you some headaches in the past. They're not that magical. So what a DSym is it's a mapping of the address to the symbols. If you build a binary just out of Xcode, it's going to include the symbols inside the binary. They do that so that when you crash while you're debugging, your crash reports include these human readable symbol names. But when you ship your program to your customers, they don't need those. Those are there to help you, the developer. But to your customer, these are a problem in two ways. The first, they're adding space to the binary. You're making your users download all of these human-readable strings when they're never going to see them or use them. Their program is only going to use the addresses to run. It'll never use the symbols. Additionally, those symbols are a map to your code. And if someone is trying to hack or attack your application, they can use that map to figure out how your program works much more easily than if they only have the addresses. To solve that problem, when we build an application for the App Store, we typically strip out the symbol names and put them into a file that we call the DSym archive or the debug symbols archive. Xcode does this for you automatically, but that file is critically important to keep around because that file will tell you what these addresses mean later on when your program crashes. So let's summarize what we've talked about so far. Programs are made up of modules. Modules load into memory in reverse dependency order. The location of the module in memory is called the base address. Function addresses are relative to the module's base address. That means the function's absolute address is its relative address plus the base address of its module. And then finally, a DSym is just a map of addresses to function names that helps you, the developer, understand your crash reports better. So we've talked about how programs load into memory. Now let's talk about how programs run. So what I've got here is I've got memory. Remember, this is linear from 0 to all F's down here. And we loaded each of these modules into memory at a specific base address. Now, the first function that's going to be called in our program is didFinishLaunching. Let's pretend that didFinishLaunching is at offset 64 in our application binary. That means the absolute address that the execution pointer is at is F00064. Now let's say one of the first things we do in our program is we want to attribute this installation to a particular ad that we ran. So we're going to call into the Facebook SDK and ask it to do an attribution check for us. That call will jump the execution pointer into the memory of the binary module for the Facebook SDK. Facebook's doAttribution method in this example is at offset 47. But Facebook's base address is F000. So we're going to jump the execution pointer to the absolute address F047. We're jumping back in memory to where we loaded the Facebook SDK. And let's say Facebook wants to show an alert view. Maybe it needs to get permission for the GPS or something. Well, to show an alert, you have to call into the Swift runtime. So now our execution pointer is going to jump again, this time all the way down into that upper region of memory where the Swift runtime is loaded. And we're going to try and show that alert view. When we're done showing the alert view, Apple's going to call return, Facebook will call return, and we're going to be back inside of the memory of didFinishLaunching, back in our application's binary module. So you can see how the execution of a program is simply jumping between these locations in memory where we've loaded the binary code. But how do we keep track of that? Well, to answer that question, we need to talk about the stack. Now, you might be familiar with a stack as a data structure where you add items and you pop items, and the last item off is the last item you put in. This is a typical interview question, right? Well, that data structure is really important to the execution of programs in modern operating systems. Every thread in your program has its own special stack memory, and that memory keeps track of any scratch variables or method calls that you make. Let's look at an example of how that might work. When your program makes a function call, we put a frame into that stack memory. A frame is just a struct with a bunch of properties. The ones that are relevant to us are the module name, the function offset, and the base address. If we call another function, we simply add another frame to the stack, but we don't remove the old frame, and so on. When we return, we can remove a frame, and we're back to where we were. In this way, the execution pointer's location in memory can be tracked on the stack, so you can call as deep as you want and always get back to where you were. So let's look at the same didFinishLaunching attribution example, but in terms of the stack memory. So when we're in the didFinishLaunching function, The frame on the stack is the main application binary. The function offset is 64, and the base address is F and 5 zeros. When we call into Facebook, the Facebook stack frame is added to the stack. Same when we call into the Swift runtime. When Swift calls return, Facebook calls return, we're back in did finish launching's memory. So the stack is helping us figure out where we are in our program at any given point in time. Okay, so I've answered a lot of questions about how programs load and run, but this is really a talk about programs crashing. So how do programs crash? To answer that, we need to mentally pause our program at a particular point and talk about the limitations we might hit. So let's pause our program at this point where we've called Facebook to do attribution and Facebook has called Swift to show an alert view. What kind of limitations could we hit at this instant in the program? Well, we could run out of memory. Maybe we've allocated a bunch of images before making this call and there isn't enough RAM left to show the alert view. Maybe we don't have a window. Maybe we accidentally made this call too early in the application's lifecycle and there's no window yet. In that case, the Swift runtime is going to call assert because you can't show an alert view without a window. We could have a memory leak and maybe we corrupted one of the strings that we want to show in this alert by writing over it. When the Swift renderer goes to show that string, it's going to call assert again as the memory is not really a string. Programs crash when they hit limitations and you don't have code to deal with it. So operating systems tell programs that they're crashing using a system called signals. I'm going to show you the Linux signal table, and I'm sure you're familiar with a lot of these. This is not all of them. And this is the same signal table that iOS uses. When Swift calls assert, it's going to send the program the sig abort signal, signal 6. Let's go through that example. So let's pretend that when we tried to show this alert view, we didn't have a window yet, and the Swift runtime used the nsassert macro to call the abort function in the kernel. When that happened, libkernel added a sig abort frame to the stack. That's what a signal is. It's adding a frame to the stack of a thread in your program. Signals are not the end of your application. This doesn't mean your program will crash. Even though that's an abort, you could handle it. If you think about it, you could have had a try catch around the block that's showing that alert view. You could catch the abort signal, log it, and just allow your program to continue running. Now, not all signals will allow you to continue running. The kill signal, for example, is guaranteed to terminate your program. But even so, you still get a short amount of time to do a little bit of work before your program ends. There are special functions that you can add in your program called signal handlers, and they can be chained to write out the memory of the stack when this happens. Frameworks like Embrace add those signal handlers to your code for you. And then our framework, when we see a signal frame like this, will write out the entire memory of the stack to disk and send that to our servers so you can look at it later. That's all that a crash report is. A crash report is the result of a signal handler reading the memory of stack to disk and then giving that to you later. So let's summarize that portion. So program execution is tracked by a special area of memory called the stack. Each thread in your program has its own stack. Programs crash when a signal is added to the stack and not handled. Try-catch finally patterns are a way to handle signals at runtime. Remember, not all signals can be handled by try-catch. Signal handlers can write out stack memory and make crash reports. This is an incredibly useful feature because it tells you what your program was doing at the point that it crashed, and that's how it does it. So let's try to put this all together. This is a big crash report I pulled off my device about a week ago. As you know, crash reports are very long, so I can't show it in full detail here, but what we're going to do is zoom in on each section and talk about what they mean. So first, this is the header. The header is just metadata about the program itself. You've got some IDs, you've got the device, version, architecture, the time that it occurred. But the most important thing you'll see in the header is the signal that happened. And so this crash report I pulled off my device happens to be a SIG abort signal. So what happened to my phone here is exactly the same scenario we just walked through. This is signal 6 SIG abort. The next section of the crash report is called the last exception backtrace. A lot of people ignore this section because it doesn't look like a traditional stack trace, but this section tells you where the exception was thrown, which can be incredibly useful. If an exception was thrown and caught, then the stack of the thread will be the catch location, the place where your catch function was. But this stack trace tells you where the exception was thrown. So if you see this in a report, I recommend you not ignore it. Symbolicate those symbols and figure out what that is, because that'll tell you which module in your application threw this exception. The next portion will be the thread stack traces. Now you should be very familiar with this from what we've learned already. What you're seeing here is exactly what I was just explaining. This is a frame number. This is a module name. This is a function offset. This is a base address. This is a line. This is exactly the same stack memory we just looked at, just written out in text form. Below that, you'll see a section on CPU registers. Unfortunately, I don't have enough time today to go into what this means. I hope to someday do a webinar exclusively on this section, as I think once you can understand what these registers mean, you can actually learn quite a lot about the execution state of your program at the time it crashed. Below that, you have this long list of module-based information. Now, this information might look useless to you, but this is actually quite critical. So this tells you exactly which slice of the binary was loaded in memory at that point that it crashed. If you symbolicate against the wrong slice or the wrong UUID, you may get valid looking symbols, but they won't be the right symbols. So you have to make sure when you symbolicate, you exactly match the UUID and architecture of the module you're symbolicating. So that's what the module-based information means. So a crash report is made up of a header, a last exception backtrace, the main thread or the thread 0 stack, all the other thread stacks, a CPU register section, which is very interesting, but I apologize, I can't talk about it today, and then the module-based information that you need to symbolicate everything else. So putting that all together, what you're seeing inside of a stack trace is exactly the same kind of stack memory we were just walking through in this talk. So here I've transcribed the first 4 frames of this particular crash into the same format I was showing you before to help you understand that these are the same thing. This stack that you're seeing in the crash report is a record of the stack memory that was actually running in your program at the time it crashed. So let's try to summarize everything before we move on to questions. The computers that we build have limitations. That's because the real world has limitations. Electricity only goes so fast. We only have so much money. Programs are broken into modules and loaded into memory. Program execution is tracked by a data structure called the stack. When programs crash, a signal is placed on the stack, and programs have a short time to process that signal. And they could even continue running if they can return successfully from the signal and it's not a terminal signal. So I hope you've learned a lot today. I know I covered a lot of ground. I encourage you to rewatch the video, internalize this knowledge, and go back and take a look at some of those crash reports that you've been ignoring for years. Maybe now that you understand what that crash report really means, those won't seem so impossible to you anymore. Thank you very much.